Here's a question. When are two types really the same? The natural numbers can be built from Pinot's zero and successor, or written as strings of binary digits. These are two genuinely different data types, yet nobody hesitates to call both the natural numbers. The real numbers are the same story. Constructed as Dijk-to-Kind cuts, or as Cauchy sequences of rationals modulo the equality that their difference tends to zero. Two different constructions, and we treat them as one and the same real line. What licenses that? In every case, there is a lossless translation in both directions, one that gives back exactly what you started with. That relationship is called an equivalence. But standard type theory does not let you freely substitute one equivalent type for another. Equivalent is not the same as equal, so you still cannot literally substitute one construction for the other. Homotopy type theory is what closes that gap. And to do it, it has to rethink from the ground up what equality even is. This is an introduction to homotopy type theory, hot. To rethink equality, we start at the very bottom. Recall that in dependent type theory, equality is not a primitive judgment, but a type. For any type A in any two elements, there is a type A equals B in A, the identity type irs. It has exactly one constructor. Reflexivity, the proof that every element equals itself. From that single constructor, the eliminator called path induction lets you prove things about every equality proof. But here's the question the rules leave open. Suppose I hand you two proofs that A equals B. Is there always a proof that P equals Q? That the two proofs are themselves equal? Asserting yes always is the principle we met last time. Uniqueness of identity proofs. UIP, the cousin of axiom K. And the crucial fact is that nothing in the rules of type theory forces it. So what if we simply don't assume it? Then the type A equals B is allowed to have genuine internal structure. The breakthrough was a change of picture found by A.H. Woody and Warren and independently by Voevodsky. Read a type as a space and a term as a point in that space. Then a proof P of A equals B is a path. A continuous way of getting from the point A to the point B. And reflexivity is just the constant path that stays put. Now, the open question has an obvious geometric meaning. Asking whether P equals Q is asking whether two paths between the same endpoints can be continuously deformed into each other. In an interesting space, the answer is sometimes no. A continuous deformation of one path into another is exactly what topology calls a homotopy. And because equality between paths is literally this, a homotopy, the theory built on it is called homotopy type theory. A proof that two paths are equal is itself a path between path, a homotopy. And proofs between those are paths between paths between paths, and it never stops. Every type carries an infinite tower of higher equalities, and that structure is exactly what mathematicians call an infinity groupoid. This is not an analogy bolted on from the outside. The operations are already there in the rules. Every equality can be reversed and consecutive equalities can be composed, with reflexivity acting as the identity. Reflexivity, symmetry, and transitivity are precisely the laws of a groupodyk. Hoffman and Streicher prove this first. with their groupoid model. Whether UIP was provable had been an open problem, and the way to settle it is to build just one model where it fails. In that model, each type is read as a groupoid, its terms as the objects, and a proof P of A equals B as an isomorphism between two objects. But a single object can carry two different automorphisms, and those are two proofs of A equals A that are not equal. So UIP fails in the groupoid model, which means it can never be a theorem. It is a genuine choice, not something the rules force on you. Homotopy type theory simply takes that tower seriously all the way up. This gives us a way to measure how complicated a type's equality is. A type is a proposition when any two of its elements are equal. That is the proof irrelevance from last time. A type is a set when any two proofs of equality are equal. And that is exactly UIP. So assuming UIP is the same as declaring that every type is flat, a set with no higher structure, Hot refuses that blanket assumption and keeps the whole tower of levels. With this picture in place, Voevodsky added the principle that gives the theory its name and its power. First, we need the right notion of sameness between types. The equivalence we met at the very start. Two types are equivalent, written A equivalent to B when there is a function between them with a two-sided inverse. A coherent generalization of isomorphism. The univalence axiom says these two notions coincide. Identity of types is equivalent to equivalence of types. A equals B is equivalent to A equivalent to B. Informally, equivalent structures may be treated as literally equal. So, the two constructions of the naturals from the opening are no longer merely equivalent. Univalence makes them genuinely equal. Any theorem you prove about one then transports for free to the other. Notice this also directly contradicts UIP at the level of the universe. A type with two different self-equivalences gives two different proofs that it equals itself. So under univalence, the universe type is provably not a set. Every construction in type theory respects equality. Why you can transport any structure along a proof that A equals B. Univalence turns every equivalence into such a proof. So any theorem proved about one structure transports automatically to every equivalent structure. Isomorphism invariance becomes a theorem, not a convention. The everyday mathematical habit of identifying isomorphic objects finally becomes literally true inside the theory. If equalities are paths, then we should be allowed to build a type by declaring its paths, not only its points. This is a higher inductive type. The circle S1 has one point base and one path constructor loop, an equality from the point back to itself. That loop is a proof of base equals base that is deliberately not equal to reflexivity. With nothing but those two lines, one can prove synthetically that the fundamental group of the circle is the integers. Each loop is classified by a single integer. How many times and which way it winds around. Topology done directly in the type theory, with no underlying notion of real numbers or open sets anywhere. There is a price, and it is the reason this is still active research. Added as a bare axiom, univalence has no computational behavior. A closed proof can get stuck and never reduce to an answer. That breaks canonicity. The property that every closed term computes to a value. The fix is cubical type theory, which builds paths from an interval primitive and gives univalence actual computational content again. This is what cubical Agda implements, so the circle and univalence actually run. All of this was consolidated in 2013 in a book written collectively at the Institute for Advanced Study. It launched Voevodsky's program of univalent foundations, a proposal to rebuild mathematics on this homotopical notion of equality. So here's the whole turn. Refuse UIP, and a proof of equality becomes a path. Paths between paths pile up into a tower. Every type becomes a space. Univalence makes equivalence the same as equality, and higher inductive types let you draw the spaces you want. Last time the fork in the road was about axiom K and UIP. Homotopy type theory is what lies down the other path, the one where equality is the richest structure in the theory, not the poorest. Thanks for watching.